Right, today we're going to be discussing Euclid's proof of the infinitude of primes. Now basically what that is it's just a proof to prove that there are an infinite number of primes. And to do that, the method of proof is proof by contradiction. There's lots of different ways of proving things in maths. You can use a proof by deduction, proof by contradiction that we're going to do today, proof by exhaustion. Another thing to mention is Euclid is not to be confused with another mathematician, Euler. It's pronounced Euler, not Euler, as Keira Knightley says in The Imitation Game. Very cringy. The proof starts off by assuming that there are finitely many primes, because remember it was a proof by contradiction. That's going to be the method, proof by contradiction. And we're going to assume that there are finitely many primes. So we're going to assume that there are only, we'll just give a number, let's assume that there are only n primes. Assuming finitely many primes. So we're going to assume that there are n primes. Now n might be 100, it might be 1,000, it might be 10 billion, but we're going to say that there are only n primes, and we're going to work from there. Okay, and we're going to start with this, do a few logical steps, and we're going to hopefully end up with some absolute rubbish which will tell us that our initial assumption of there only being n primes, or a finite number of primes, must be false, and therefore there must be an infinite number of primes. That's how the proof's going to work. So we're going to assume that there are n primes, okay, and let's give them names. We'll say that these n primes, the first one's P1, second one's P2, P3, all the way up to the nth prime, which we're going to call Pn, prime n if you like. Okay, and the proof goes like this. We come up with a construction, okay, we call it C. We'll say that this number that we're going to make using these prime numbers is basically the product of these n primes. So P1 times P2 times P3, as you're aware in algebra, you can just write them next to each other if you want to multiply them. Multiplied by all the primes up to the nth prime, so all of them multiplied. I'm going to add 1. And this is the very clever bit about the proof. So we're adding 1. And now this number is either going to be a prime number or it's not going to be a prime number. So we've got two cases then. C is prime, or C is not prime. We have a word for that. It's not prime, we call it composite. A composite number just means that it's composed of other primes. For example, 15 is not a prime number, but it's composed of the primes 3 and 15. 5, silly boy. 3 times 5 gives me the 15. Every number bigger than 1 is either going to be a prime or a composite. Can't be anything else. So we've broken it down into two cases. We're going to deal with one at a time. So let's assume then that C ends up being a prime. Well, what then? If C is a prime, well then we've kind of already disproved it. We've already gone against there only being n primes. Because at the start, remember, we said there were n primes, but this number that we've made is clearly bigger than, well, it's clearly bigger than the biggest prime, which was the nth one, because I've multiplied this prime by some other positive numbers, positive integers, and then I've added 1. So this C, if it is a prime, it's going to be bigger than all of these other ones. So I've just ended up with a prime that's bigger than the original n. Therefore, this leads to, so that's obviously a problem, leads to a contradiction. All right, that's good. Now we're going to look at this guy. And now hopefully we can use some logic to prove that this would also be incorrect. And if that's the case, then we've proven that we've proven that there are an infinite number of primes. All right, so this was just an example, by the way. If you want an example of sort of this situation, where this situation could arise, is if we took n to be 3, we'd get 2 times 3 times 5. 5 is, of course, the third prime. You add 1 and you get 31 to this. And 31 is another prime. And of course, if we assume that there were only these 3 primes, but now we've ended up with another prime, that's of course a problem. It goes against what we originally said of there only being 3 primes. So that of course can't be true. For the second case, if I assume that C ends up being composite, well then what that means is it's composed of some primes. Of course, if it's composite, it can't actually include any of these numbers in any of these primes in its prime factor decomposition, because C is 1 more than a multiple of P1. Therefore, it can't be a multiple of P1 because it's just 1 more than it. For example, 13 is 1 more than a multiple of 2. Therefore, it can't be a multiple of 2. And since every composite number has a prime factor decomposition, we've just said that its prime factor decomposition can't actually include any of these primes, because C is always going to be 1 more than a multiple of any of these primes. And to see this in action, let's have, say, n equals 6. If n equals 6, we get 2 times 3 times 5 times 7 times 11 times by 13 plus 1. And this is a really big number. It works out to be 30,031, which is actually 59 times by 509. So the prime factor decomposition of this number actually contains primes that are, again, outside the original list. If we assume that there were only 6 primes, and I try and make this construction, what I end up with is a number that contains primes that are outside the original list. So again, it leads to a contradiction. And it says basically that there can't be a finite number of primes because I'm always going to find primes that are bigger than this original list. And that's how this proof works. And of course, this also is a cross, leads to a contradiction. And that's really all there is to it. So if there are any questions, please leave a comment. Other than that, I hope you enjoyed the video. Thank you. Bye-bye.